is Marcella Wijngaarden from the University of Amsterdam, and she will talk about Speckle Interferometry. So everybody greet Marcella. Perfect. Can you see us?
I can't, no. I see my slides.
Ah, okay. So, okay, it's yours.
Okay, thank you for introducing me. I'm very happy to be talking to you all the way from Amsterdam and to be part in this wave of the conference. I hope you've been having a very good and interesting time so far. So as Marek mentioned, my name is Marcella Wijngaarden. And I study and work at the Anton Pannekoek Institute for Astronomy in the Netherlands. And today I will talk to you about Speckle Interferometry for binary star observations, and in particular about the technique of full aperture speckle interferometry. So let's begin with a quick overview of the talk. I will start with an introduction. I will give a few reasons on why we should study binary star systems, why are they interesting, and then why speckle interferometry is a good technique to do this. Then, of course, we'll talk about what is speckle interferometry. We'll just go through some theory and also observations, data reduction and calibrations. And I'll end with showing you some of the applications, and also I'll show you some of the applications that we do at Anton Pannekoek Observatory where I work. So, why study binary stars? I heard that some of you are already interested in binary stars, so I probably won't have to convince you too much, so we'll just go through it quickly. But the first reason, in my opinion, has to do with stellar evolution models. And they are often visualized as an Hertzsprung-Russell diagram, as shown here on the slide, where you see the luminosity and the temperature of the stars. And this shows how we think how stars evolve through time. And one of the most important properties to derive this and to describe this evolution is the mass of the stars. And the mass of the stars can only be determined by analysis of binary star orbits. So it's very important that we have good observations to test these models. And also, it's actually for the most common stars in our universe, and for massive OB stars, the mass is still not well known. And this is actually one of the open problems in modern astrophysics. So the next reason why binary star systems are interesting is because they play an important role in many theories of interesting astrophysical processes. For example, they are the originator of type 1a supernovae. Also an interesting process is neutron star accretion, which happens in binary star systems. They play an important role for black hole formation and also neutron star formation. You can see an example here on the slide. Also, which I think is an important issue, there is a big lack of observational data of binary star systems. So there are over 100,000 systems in the Washington Double Star Catalog, the WDS, which is the one of the largest catalogs for multiple star systems. And only of the order of about 100 systems of them have grade 1 orbits. And grade 1 orbit just means that the orbit is very well described, so we have full coverage. So there's much data needed. And also to complement space missions. For example, we have the Gaia mission that will have its first data release this year. But to describe binary orbits, we need good time coverage. So still, even with the space missions, we need observations from Earth-based telescopes. So these were a few reasons why we should study binary star systems, and now let's talk a little bit about why speckle interferometry is a good technique to do this. And in order to do that, we need to talk a little bit about what limits the resolution of our telescopes. Because for binary star observations, you want to have the highest resolution possible, so you can distinguish the closest binary stars possible for your system. You're probably all familiar with this, but we'll just go through it quickly. The first limit is, of course, the diffraction limit, and it is determined by the size of the telescope. And this limit arises because light will get diffracted at the edges of your telescopes, as is shown in these pictures as well. And for larger telescopes, for larger apertures, the fraction of the total incoming light that gets diffracted is smaller, and thus a higher resolution is possible. Another way to think of this is that the ratio of the edge of the telescope to the total size of the telescope aperture is smaller, so of course less of the light gets diffracted. Then secondly, for all Earth-based telescopes, we have the seeing limit, and this is set by atmospheric distortion, and we'll talk more about this in a minute. And this is actually the most constraining limit for larger telescopes. Alright, so the seeing limit is set by the atmospheric distortion. And this just means that as the light comes in from an infinite distance, as is shown in this picture, it can be regarded as a plane wavefront. And a plane wavefront just describes all the points where the incoming light has the same phase. But as it goes through the Earth's atmospheres, the wavefront gets distorted, as can be seen in this picture. And this is because the atmosphere consists of small packets of air that change the phase of the light differently. And these air packets in the atmosphere change on a characteristic timescale, which we will call T0. And we will come back to this timescale when we discuss the technique to overcome these atmospheric effects. So let's have a look at how these limits on the resolution of our telescopes look like in pictures. Here you see on the left a short exposure image with a small telescope. And when I say small telescope, in this case, I mean a telescope of about a diameter of 10 centimeters, so really small. And you can see that for a small telescope, diffraction rings will form around the central peak. So we can see clearly that the diffraction limit is ruling here. In the middle, you see a short exposure with a larger telescope, and larger just means that it's larger than 10 centimeters. And you can see small dots. And these are called, I hope it's clear for everybody in the room, but these are called speckles. And they are the result of the incoming light going through the different air packets and just landing on different places on the detector. And the image on the right, you can see how longer exposure is just a combination of all these speckles and results in a blurred image. So you can see from this picture that we do not reach the theoretical diffraction limit of our telescopes if the telescope is larger than 10 centimeters because of atmospheric effects. And this is very unfortunate if you want to distinguish binary stars. And this is where Speckle Interferometry comes into play, since Speckle Interferometry is a technique to overcome the blurring effects of the Earth's atmosphere. So, what is Speckle Interferometry? Let's talk about how it works and how you can use these techniques. The basic idea behind Speckle Interferometry is to take multiple short exposures. Usually you would take about 400 frames with exposure times that are smaller than 10 milliseconds. And it's smaller than 10 milliseconds because this is the variability timescale of the atmosphere in the visible light. So the idea is that in these frames you actually freeze the atmosphere so that it's no longer changing within the time that the image is taken. So in all of these frames we see multiple speckles, and the idea is actually that the most occurring separation between the speckles represent information about the components of the binary systems. And we can use then statistical analysis on all the 400 frames to retrieve the most important information to describe the orbit. And this is the position angle between the components and the separation between the components. And this is just a very basic idea behind the technique. And I hope in the next few slides it will become more clear. Because to really understand what is going on, we need to go through a little bit of math, But it's not important to understand the formulas completely as we go through them. It is more important what we can learn from them and how we can use them easily. So each of the images I just showed in the previous slide can be expressed as a function, which is shown here on this slide. And this function consists of two components. So you see the p there, that is the point spread function. And this just describes how the light of the point sources is distributed across the image. And this function is then convolved with functions that describe the true intrinsic shape of the light of the object. And what is important to take away from this slide is actually that we assume the point spread function to be constant during each exposure. So we assume that it doesn't change when one exposure is taken. So as I said, we assume that the atmosphere is not changing within that time. And this is actually the reason why we need to take such short exposures. Okay, so to simplify our calculations, we do a trick that you usually do if you want to simplify complicated calculations. We transform our functions to Fourier space. Because in Fourier space, we have a multiplication instead of convolution between the point spread function, which is now called the transfer function, and the object function. These are just the same functions as we saw before, but with a capital letter which just denotes that they are Fourier transformed. Okay, so now you may be thinking that it's nice, all these formulas, but how do we get to information from the binary system from using them? And we'll just go through the simple steps. So first, it's important to realize that for a binary image, there are actually two overlapping object functions that we want to have information about, as you can see on the left. So it's the same function as before, but you have now two object functions. So you actually have two overlapping speckle clouds in your image. The second step is to rewrite these functions in terms of the separation between the object functions in pixel space, as is again shown on the left. And it's not, I understand it's a lot to go through, but I just put this formula on for anybody that is interested. I will post it. And then we take, as mentioned before, we take the Fourier transform to, so now we have an image that is described as a function that has both an amplitude and a phase. And for full purchase Speckle Interferometry, we are just interested in the amplitude at first. And we will take the square of this function because this can be easily related to a power spectrum, which we will see in the next slide. And notice here that we ended up with a cosine function, and this will help us later on. Because here you see above you see the same function as before. And by using the speckle frames of also a single calibration star, a reference star, we can obtain the point spread function and use the middle formula that divides the average of the image functions by that of the average of the reference star functions. And the resulting image you see below, and this is called the power spectrum. And here you see how the fringes, how there are fringes with light and dark bands, and these are described by cosine functions such as we are seeing above. And it's actually possible to obtain information about the binary components directly from this image, but usually we go one step further and we calculate the autocorrelation. And this is the last step really. So we use the power spectrum to calculate the autocorrelation. And an example of an autocorrelogram is shown in the lower right image. And I'll just explain what this means. So the pictures above, the two pictures above, they represent the speckle frame and with the most occurring separation indicated. So for the left image, this would be the separation between the black and the white dots. And then what you do is when the separation and orientation for each of the pixels, which each of the other pixels is calculated, then we retrieve the picture. So you see a central peak and two peaks on the side. And the two bright peaks on either side of the middle, they denote the most occurring separation and orientation. Okay, so how do we derive binary properties from this diagram? The separation between the two peaks, so one on the side and the middle peak, is that of the binary, but then in pixel space. So we have to convert them to, for example, arc seconds, and then we need to know the plate scale of the system. So we need to know how many arc seconds is covered by each pixel in the frame. And in the same way, we can derive the position angle from the angle between the peaks. Of course, then the image orientation must be known as well, in order to know which way is north and east and so on in the image. And I would just like to emphasize here that this autocorrelogram is not an image of the two stars, since for that we need information about the phase as well, and we disregarded that in the methods earlier. But there are also a little slightly more complicated methods to also retrieve the phase, and we will see examples from that later on. And also what you can see here is that there is an 180 degrees ambiguity. And this is because the separation between two pixels is calculated twice, one time for each of the pixels. And therefore we have two peaks on the side of the central peaks. But fortunately there are numerical techniques to overcome this problem as well. So just a recap of the method. We started with taking a lot of very short exposures. We took the Fourier transform of those exposures as shown on the left below. They were used to calculate a power spectrum, an average power spectrum. And the power spectrum was used to calculate the autocorrelogram on the right below. And from the autocorrelogram, we derived the binary properties. So this is the theory. Let's talk a bit about about how to do these observations. And let's start with some instrumental considerations. So larger telescopes for Speckle Interferometry produce smaller airy disks and more speckles. But you need enough non-overlapping speckles in order to do the methods we just described. So we need to use magnification techniques or shorter exposure times to get enough of these non-overlapping speckles. But in this way, larger telescopes lose some of their advantages. Of course, they still have better resolution, but it's not necessarily, it's a trade-off really between the size of the telescopes. And this is actually what makes Speckle Interferometry a perfect technique for amateur-sized telescopes. You don't need a very large telescopes, and you do not need a complex setup. So as I mentioned here already, we need enough non-overlapping speckles, and in order to get them, even for amateur-sized telescopes, we can use techniques such as eyepiece projection. So because we want, it is experimentally determined that it is best to have an airy disk size of about 10 to 30 pixels. And in order to get that, we can use projection techniques. Because this, of course, increases the focal length of the optical system, and with that you get a larger magnification. As is also shown by the formulas below. You see that the effective focal length determines the size of the airy disk in the top formula, and in the bottom formula you can see that you can have a larger effective focal length by using an eyepiece. I was going to discuss a little bit about the speckle setup that we have here at the Anton Pannekoek Institute that is shown here on the slide now, but in order to stay in time, I think it's best to skip ahead. But if anybody is interested, I'd be happy to explain more about this later. And then let's move on to the data reduction. because the most important things we already discussed in the theory section. But an important thing is that the quality of the result heavily relies on how well the image is calibrated. So you really need to know the image skill and the image orientation of your system. And there are several methods to do this, perhaps you're familiar with them. One obvious one is to use calibration pairs, so you use binary pairs with known separation and position angle. And you use these images to calibrate the plate skill and the image orientation. Another way could be to use drift analysis. So you have a single star on the side of your image, and you switch off the mount motor, and you analyze the star trail. And you can derive which way is east and west from that. So, of course, you can write your own reduction routines based on the theory, but I would want to mention here that there's very good software available and very easy to use, and also free software. So, for example, Reduc by Florent Loss, there's Platesolve 3 that is slightly more professional, and there are several Python routines. And I would encourage everybody to give it a try, because these software they do all the theory steps for you. So you just do the observations and make sure your system is well calibrated, and then you can use the software to easily retrieve the binary star information from that. So some applications. Of course, the most obvious one is that, at least in this talk, is that they can be used for refining binary star orbits. Here on the left you can see an image of an orbit taken from the WDS catalog, where you see that the blue dots, they represent speckle measurements. And these speckle measurements are really one of the best quality measurements that are used now for binary star orbits, and they are used to refine these orbits that are known. And they use both amateur and professional data. This is really a field where both play an important role. So as I mentioned earlier, by the techniques we described, we didn't retrieve an image, but there are also techniques where you can retrieve the phase information. Knox-Thompson techniques, they're called. And I just wanted to show you a very nice example of this that I found on the internet, where here on the left you see the speckle frames, and here on the right in the smaller image you see the reconstruction of the image. And you can really see two small components appear, and you wouldn't imagine maybe initially that from these frames you could get such a high quality diffraction limited image. Yes, to end with, I wanted to show you this picture of our observatory. It is located very near the center of Amsterdam, and you can see it's a horrible site to do astronomy. We have a lot of light pollution, and we have very bad seeing. And the point that why am I showing you this picture? It is really to encourage you, because if we are with Speckle Interferometry, at such a bad site, we are able to do good quality Speckle Interferometry observations, binary star observations. So if we can do it here, you will probably have better conditions in another place, so you can definitely use this technique. So yes, as I said, we have bad seeing and a very bright background. One of the things that we are currently doing is we are trying to set up a semi-automated Speckle Interferometry program that can be used for student observations. And these students from the University of Amsterdam can then actually contribute with their observations to binary star science. So just to conclude with, Speckle Interferometry is a method to approach the diffraction limit of the telescope, so to overcome really the seeing and atmospheric effects. It's a method that is accessible to both professionals and amateurs. There are other methods that overcome the seeing, such as adaptive optics, but they are really expensive. So this is really a cheaper way, a cheaper alternative that can be used by more people. And there are a lot of interesting applications possible. I don't know how I am in time, so if we have enough time, if we have a lot of time for questions, but I would really like to encourage everybody to contact me. I put my email below here on the slide, and I'd be very interested to hear what you are thinking, and maybe if you're interested in using these techniques, I'd be very interested as well. So thank you for listening. This was my talk.
Thank you very much
a little bit, yes.
Yeah, you were perfectly in time, so we have a few minutes for discussion and questions. Are there any?
I have a question, Miroslav Smolka from Slovakia. So you mentioned that there are optimal, I would say, that it is possible to measure this technique in with amateur-sized instruments. Is there something like an optimal combination of technical parameters like pixel size?
Sorry, I cannot hear you very well. Could you repeat the question a little bit louder? Or?
Hello, can you hear me now? Hello? Hello?
Hello, yes, now I can hear you.
Okay, how it works. Okay. So my question was that is there something like an optimal or minimum combination of technical parameters of amateur instrumentation like diameter of objective lens and focal length and pixel size to get useful results? Because you mentioned that this technique is within the reach of amateur instrumentation.
Yes, definitely. So there's been a lot of experimenting with different setups and different parameters, but really it depends on the system that you want to observe. For example, for wider binaries, you can use smaller array disks. It's better to use smaller array disks than for closer binaries. But often with amateur systems, and also actually with professional systems, you are limited to the instrument you have. For example, you could vary the distance between the camera and the eyepiece to change the array disk size without using different eyepieces. But then you need a system where you are able to actually change that change that distance, and often it is not possible due to the limits of the instruments that you are using. But there is no one optimal distance known, because it depends on the separation, for example, of the binaries, but also the brightness of the binary, and also the if they have the same brightness, or if one is much brighter than the other, then that affects what would be the optimal system to observe with.
Okay, and are there any published?
I hope I answered your question.
I just want to ask you if there is any published. Hello? Okay. Hello, does it work?
Yes.
Okay, sorry. So my question is if there is any published source of information how we can derive, I would say, parameters of our system to achieve a certain level of precision to observe certain type of binaries.
Okay, yes. A very good resource for this would be the Journal of Double Star Observations. And there's recently Russell Jennett wrote a book about this. And if you want, I could provide some of the articles that are about this subject, and also some of the books. I could send them. I could send you the links if you are interested.
Yeah,
thank you.
Just let me know your email address. Send me an email, and then we'll do that.
Yeah, we have your address, so
yes.
wouldn't be a problem.
Okay, good.
There's another question.
Yeah.
Hello, this is Rainer Auer speaking. You spoke about Gaia and its data, but you're still interested in even more data from
Sorry, the last part is not coming through.
Yes. Okay, I repeat it. You spoke about Gaia data, and you need more data even from amateurs. Are you going to create some kind of program to lead amateurs what stars they should observe?
That's actually a very good idea. It's mostly, I'm not sure if there are, there are already some groups of amateurs together with professional astronomers that talk together about what are good sources to observe. But I'm not sure if there's one source of this information. Of course, it are often the wide binaries, so with large periods that need also much data from amateurs, because Gaia won't have the full coverage of their orbits. But if you're interested, then I can also send information about what are good sources to observe to anybody actually that is interested. I would be happy to do this.
May I have one more question?
Of course.
I refer to the gentleman who asked before. So if you combine type of stars to be observed with needed equipment, size of telescope whatsoever, that would guide amateurs to in their decision what to do.
Okay, you mean information about how to set up your system, where you can find this?
Yes, you explained that depending on the distance between the binaries, you need different equipment.
Oh no, not necessarily different equipment. Sorry, you can use the same equipment to observe both systems. But the question before, I think, was what would be the optimal configuration of your system, and it would be slightly different depending on both cases. But even so, with the same system, you could observe both separations.
Okay, thank you.
Are there any other questions? Yeah.
Hello, this is Zíbar speaking. Thank you for a very interesting speech. My question is, if I'm not mistaken, your math is developed for distinguishing of two stars, but in area of eclipsing binary stars, we sometimes need to distinguish when or to distinguish if the particular star is a blend with another star. Is there any math developed to use this technique for searching for some close companion which is normally hidden in seeing?
Yes. So it is more challenging, of course, but the math also applies for other types of sources. For example, it can be used also for extended sources in a way that they use sum multiple point sources and just to describe an extended source. And it could definitely be used also for multiple components, so more than two. Definitely, yes.
I'm not sure if I explained it well. I don't mean distinguishing more than two sources. I mean decision whether the observed star is a double or single. If there is a blend of
okay, yes. It is actually, Speckle Interferometry is also used indeed to discover to test single stars for if they are actually binaries or multiple star systems. Yeah. this is also an application for this technique with the same map actually.
Okay, thank you.
Yeah, thank you.
Okay, any other questions? Maybe I have one. If you use so short exposures, what equipment do you use, and what's the magnitude limit you can reach with your half-meter telescope with these very short exposures?
Yes. Okay. So we are still pushing our limit, but what we have observed with our half-meter telescope, the limit is really 8 magnitudes. But also here it is important whether the two stars have the same brightness or different, because if they have the same brightness we can go up to we can go now up to 10, but if one of them has magnitude 10 and the other has magnitude 2, then it becomes more difficult, because then it's harder to detect the dimmer component.
Okay, thank you.
So yeah, sure.
And if there are any other questions, so we would like to thank you very much for your interesting talk, and
thank you. and again, I want to thank you as well, and I hope you will contact me because I'd be very interested to discuss this further with anybody.
Yeah, I think that at least two men will
Yes,
contact
very
you.
good. Very good.
So have a nice day. Goodbye.
Yes,
Thank
the
you.
same. Enjoy the conference.
Thank you. Bye.
Bye.